we are people and we're organic systems. We like certain amount of comfort, and there is definitely a range of comfort that we are used to. Yes, there is acclimatization. So, you know, people who are, for example, if you go during the winter to South Africa or you go to Egypt, and you'll see they are wearing heavy clothing and knitted stuff. Yes, for them it's cold. For us, it still is very comfortable. But in terms of human comfort and what we are expecting, it's a very limited range. We really, because of our lungs, we prefer humidity levels between sort of a range of 50 to about 60% relative humidity. And again, our lungs are best functioning when it's also reasonable temperatures. But the whole thing comes down to the thing that our environment is made by our surrounding. And if we are thinking in terms of our buildings, the buildings are contributing towards our environment. Yeah? Many of you would have heard of thermal mass and other things that buildings actually contribute towards things. But a quick recap on materials. Two types of building materials, mineral and organic. And within both of those, we can have both of those, whether they're material, mineral, or organic, being heavily processed to turn it into a product which often enough doesn't even resemble the original material, to a level of where the material, just like the structure of this, you can easily recognize timbers here, right, that have been roughly shaped for the purpose. Now, if we are thinking in terms of how those materials are performing within our environment, it's very important to understand that. And we need to understand that those materials degrade, right? They degrade because of our environment and because of the way we are using the internal environment. Yeah? Now, with most materials, if you think in terms of them creating an envelope around us, all of those materials have to allow moisture to move through. This is not damp, it's water vapor. Most of those materials have to be water permeable, but there is a slight problem as well. As that moisture moves through the building, it also has dissolved oxygen in it, dissolved carbon dioxide in it, so it's slightly acidic, okay? And in terms of what happens in the cavities, this can create a problem for metals as well as timber. Timber, by its nature, is hygroscopic. It likes moisture. It likes to absorb moisture. Okay? And when it absorbs moisture, and when it reaches approximately 15% moisture content, it becomes very delectable to things called fungi, right? And once the fungal attack commences and the fungi die, they leave behind oils and proteins, which then the insects can really enjoy, okay? Because they'll get their proteins, and then the remaining cellulose, which is sugar, okay? So your main dinner followed by dessert. Wonderful, isn't it? So, what do we do to prevent that? Well, people call it treating. No, it's not treating. Forget about that word. It's called poisoning, right? If it's poison to fungi and it's poison to insects, it's also poison for us, okay? A lot of those treatments, they leach out. They end up in our environment, okay? So if we are using timber, really we need to use timber as pure timber without so-called treatment, okay? It doesn't help us. So, but moving on, one of the things about the UK housing stock, we have a lot of old buildings. These old buildings are also the buildings that are probably one of the poorest in terms of energy conservation and in terms of their construction to resist external elements. And unfortunately, those are the buildings that end up with the lowest energy performance certificates, okay? So the new owners inevitably move in and they try to improve those buildings, refit them, retrofit them, refurbish them to bring them up to some kind of a comfort level that is suitable to people. And one of the things that EPC certificates will mention, it will mention that the energy rating is very low in those. And when people start talking about energy rating, they start talking about U values of the walls and of the roofs, okay? And U value is the basic resistance of the structure to passage of energy, right? Insulation, what it does, it slows down the passage of energy, right? It takes longer for the energy to escape the environment. Now, if you do a quick search, and this is the quick search, 611 million results for U value calculated, okay? Many of those will do a reasonable U value calculation for you. So all you do is any one of those, just input the information and it will give you a U value calculation. But this is not quite all it's cracked out to be. A U value is only an indicative thing, right? Because if we are looking at the whole thing in terms of the structure, there are many, many different elements within the same area. Because if we are calculating plaster, brick, cavity, insulation, brick again, well, if we shift it just by 75 millimeters, what you get is plaster, mortar, cavity, insulation, mortar again. Shift it slightly over and you will have plaster, mortar, metal, mortar, yeah? Because of the wall ties. So if we do calculate things carefully, the U value that normally these softwares calculate, they're completely different to actual calculation of the U value. But I've been involved in doing thermal calculations for buildings since 70s. Why? In the 70s, at the university, they were scaring us with the second ice age. Yeah? Seriously. There's articles from 70s, we are expecting ice age. Within sort of a 10 years, all of a sudden it moved to global warming. Yeah? So all of these things is the way politicians really want us to think, right? It's not what's happening out there, it's what they want us to think about. So In mid-80s, I returned to UK in 81, but in mid-80s, I ended up going to Milton Keynes, where the early standard assessment procedure for thermal resistances was being discussed. Because Milton Keynes development corporations, they were always trying to create these buildings of the future, and they were looking forward to creating a much better environment for the building. So this is when I really got excited. I thought, okay, need to do a bit more about that. So I started working on a spreadsheet, which a simplified version I will show you, all right? But the more important thing is I'm not going to be talking about the U value. This is immaterial. What I will be talking more about is what happens to the moisture in our environment as it moves through the building structure, right? This is the one that can do inordinate amount of damage, and people don't realize what happens with it. So, as we are looking at the building fabric, it's comprised of different elements, and each one of those elements has resistance value, all right? And that resistance value is normally noted as R or lambda. How many people like sciences here? I love sciences. It gets even more interesting when you go into it in detail. But as each element contributes certain amount of resistance, what happens is that it creates a gradient in temperature drop. Next time you open up a window in the morning in your bedroom, put one hand on the inside surface, one hand outside. Just don't lean too much out so you don't fall out. And you'll notice that on the outside it's colder, on the inside is warmer. Right now, do an experiment. You're sat on a chair which has metal legs and a cushion. Put one hand on a cushion, one hand on the metal leg. Which one is colder? Metal leg. No, it's not. Ambient temperature, exactly the same. But the difference being is that the metal is about 60 to 70 times more conductive, so it takes the heat away from your hand much quicker, so you perceive it as colder, right? But ambient temperature, exactly the same, right? And this is structural gradient. As the temperature drops from, let's say, 20 degrees inside to 0 degrees outside, okay? So something is happening within that structure. And it's called structural gradient. Now, the one that we really are concerned with is that one against that one, dew point gradient. And what is the dew point? Today, you finished, you got home, you're going to drop a few ice cubes into a glass, pour some whiskey on top, a little bit of water, and your glass starts to condense on the outside. It's reached dew point, right? So the water is condensing. So what is happening is that the dew point gradient and the structural gradient, when those two are mixed together, they can create a problem for us by creating interstitial condensation. How many people have heard about interstitial condensation? A few people, quite a few. Oh, excellent. I will make it much clearer as to what happens with the whole thing. So, but it's got to do with this lovely graph. Isn't it wonderful? It's beautiful. Psychrometric chart. Logarithm based. Not base 10, it's base 2.718, blah, 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 blah. Right? So, all of those lovely curves derived from logarithms. And guess what? It was a lot of empirical work that went into it and plotting it and everything else. And this one is the one that I like. Why? Not only does it give me dry bulb temperature, but it also gives me the dew point temperature, which is important. We have a device called a hygrometer, which is two straightforward thermometers next to each other, but one of them is surrounded, the bulb is surrounded by a wick, which is in the water, and as water evaporates, it registers dew point temperature. So the one with the wick is registering dew point temperature. The one without the wick registers the dry bulb temperature. But what's it got to do with the whole thing? First thing first, if we're looking at the temperature here, 25 degrees, as we go up, can you see the curves? This dew point means 100% saturated. No more moisture can be carried at that temperature. So, if we're going right up to the top, and there it is, that is 20 grams of water per kilogram of air, right? And as we have more water particles, these water particles are excited, they're impacting each other, so they're creating pressure, vapor pressure. So the warmer it is, the more water is in the air, and the higher is the pressure. The colder it is, there you are, 0, if you go along that line, yeah? And this is, how many people are aware of air source heat pumps? Yes? COP, coefficient of performance? Yes? Guess what? The air source heat pump draws air through it, but it's not the air particularly that it needs. What it needs is the moisture in the air. And as temperatures drop, there is less and less and less moisture in that air. So what happens is that the COP performance drops as well as it becomes colder. So at a certain point, you're 1-to-1. So whatever electricity you're putting in, this is the energy you're getting back from it. Until it gets colder, you're putting more electricity in than the energy you're getting back. Because basically there's very little moisture in the air. So, as the moisture levels go up, the vapor pressure also goes up. So, we want to find out the relationship between those. And it's quite straightforward. Let's say 50% relative humidity, 24 degrees, dry bulb temperature. We want to know what would be the condensation point at that. So, there's the 24 degrees, 20, 21, 22, 23, 24. Go up to 50 degrees. Yeah, this is 50 relative humidity, right? From there, we can go across and calculate the vapor pressure in millibars. But most importantly, if we go at an angle, we will find out that the dew point temperature is 15, 16, 17, 17.2 degrees approximately. So, if at 50% relative humidity, dry bulb temperature is 24 degrees, if your walls are internal surfaces at 17.2 degrees, guess what's going to happen? The water will start condensing on those areas, right? Surface condensation is created, okay? Now, and this is the problem that a lot of people will encounter and say, I have dampness, I have mold and mildew growing in my walls, right, because of the surface condensation. Often enough, it's not only the surface condensation, it's actually the interstitial condensation that contributes tremendously towards it. But this will all get a bit clearer. So, what happens next? If we went straight across, we also will get the relative vapor pressure at this point. And that will help us to understand what is happening in terms of resistance of the building fabric to the passage of moisture. Because what's happening inside is warm environment and high levels of moisture. That vapor wants to move outside to regularize the pressure between the inside and outside. So there's got to be pressure inequality for it to happen. And this is where our building fabric has to be porous to allow that movement, right? If it's not porous, all of the water will get trapped on the inside because it's got nowhere to go. So, this is simplified spreadsheet, by the way. And what is it simplified spreadsheet of? This is straightforward 9-inch brick wall, traditional Victorian building. Skim, plaster or render, right? 3 millimeters of skim, 13 of plaster or render, brick, 9-inch. RSI and RSO is a layer of air that basically has stalled against the inner and outer surfaces, right? So, next what happens is that we assign values for it, and all of those values, they come out of the tables that are produced by scientists through experimentation, and those are resistances values, but then R or lambda factor is applied to actual physical elements. So 0.81 for skim, 0.85 for plaster render, brick 0.84, and by the way, the smaller is that number, the better is the insulating value. Okay? So adding and assigning the resistance value for the thickness of the material, because those values are per meter thickness of the material. So quite straightforward calculation. It reduces 0.85 to 0.04 and so on. And then added all up, reciprocal of that gives you the U value. Okay? As straightforward as that, simple. But now comes the interesting part. As we apply the element of resistance, what we are doing is apportioning resistance of each layer relative to the total resistance. So we start with the air layer on the inside at 18 degrees. Outside, so temperature inside 18, temperature outside 2 degrees. So on the inside 18, as soon as we have gone through the stalled air layer, the temperature drops. It drops again through skim. It drops again through plaster render, drops quite significantly through brick, and then it reaches 2 degrees at it reaches outside. So then we get that plotted. Okay? Blue is the structural gradient as the temperature drops. Now comes the next thing, and this is excited molecules of vapor in the warm environment. Again, we have resistances values for different materials, and different materials behave differently. For example, skim is, this is the value, meganewton seconds per gram, and those are the values straight out of the tables. And again, we reduce that for the thickness of each layer, and looking at psychrometric chart, we can calculate the pressure drop within each layer of the material. And by looking at the pressure drop and going, remember psychrometric chart, going at an angle, we can work out the dew point gradient going towards the saturation curve. And if we plot that, this is what it's telling us. So it's telling us that in a standard Victorian building, your dew point gradient is below your structural gradient. What does it mean? It means that there is condensation happening at this point where, in effect, your brickwork is finished. Okay? That's where it starts to equalize. All right? So Victorian building allows moisture to move through at a reasonable rate without creating any problems. Okay? Nice. In comes a new resident. And this new resident calls in a builder. And the builder says, oh, we're going to sort it out, we'll make it warmer, and what we will do is, on top of your brick, we will put some insulation. So we will use some 2x2s, yeah, 50 millimeter. And in between the 2x2s, we will put some rock wool, plasterboard over the top of it. Wonderful. Straight away, if you do a U-value calculation, 0.365, you've gone from 2.2 to 0.365. Hey, this is 1/9 value of the previous one. So in terms of energy, it's wonderful, isn't it? U-value, you've improved it. Yeah? There's a problem. Your structural gradient now, and there's the calculation for the structural gradient. Again, you can see what's happening here, that 17.13 degrees, all of a sudden, through the rock wool area, it drops down to just below 4 degrees. So this is the biggest drop that's happening through rock wool layer. Okay? Important to understand. Then we do the vapor resistance. Now, this is vapor resistance for different values, and vapor pressures, and the corresponding dew points. And we plot that. And what's happening is, can you see that the dew point gradient is all of a sudden above the structural gradient? What's it telling me? It's telling me that condensation is happening within that boundary. So where previously the condensation was really limited to the outer face of the brickwork, it shifted it over into the brickwork and into the actual insulation layer. Look, this is insulation drop. It's in insulation layer that the condensation, interstitial condensation, is happening. Yeah? Okay? So your brickwork and your insulation are actually collecting moisture inside them. Okay? Not a good thing. Why? Within that area, you have that rock wool, which is good. It's inert. But in between the rock wool, what is the plasterboard fixed to? Timber, 2x2, right? So, if you're using plain timber, unpoisoned, it's fine. But if you're using timber that's been poisoned, that moisture allows the chemicals to leach out, okay? Not a good scenario. So, not a good approach. The next one comes along and says, okay, now we're going to do it slightly better. And this is, remember, this is simplified version of the whole thing. Now we're going to do exactly as we've done before. We'll put 50 by 50 timbers, rock wool in between, but underneath the plasterboard we will introduce membrane, polyethylene membrane. This is often done. Everybody has seen it. Well, guess what happens if we run the whole thing through? First thing first, this damp-proof membrane, it's about 10,000 times more resistant to vapor pressure than even brick and concrete. Okay? So it doesn't allow any moisture to migrate across. And what it does as a consequence is drops the dew point lower and brings it back almost to the reasonable level of the standard Victorian construction, where your dew points start coinciding on the outer face of the brick. So it's good, isn't it? Yes? Using vapor membrane. What happens next? There's a guy that comes along and he carries those long copper things that are quite straight, called plumbers. Yeah? They'll drill a hole through that, and then there comes along the other guy that has those long copper things with plastic over the top that are, you know, sort of bundled in around things, called electricians. Yeah? And they all come along and breach that dozens and dozens and dozens of times. So, unfortunately, that idealized situation doesn't happen. So, unless the membrane remains integral, that doesn't happen. What happens is a really nasty situation that, just like a dam, if you have a small breach in a dam, the water pressure will breach the dam. Okay? Exactly the same with vapor, right? What happens is weak areas will conduct the vapor much faster. So, ideal situation, if you manage to have the damp-proof membrane intact, excellent solution. If not, it doesn't work. Rock wool, rock wool, rock wool. Wonderful material. Why? It's inert. It doesn't have cells, so it's free draining, as opposed to most of surveyors specify cellular plastic insulation, right? This is plastic. It has air blown through it to expand it and introduce bubbles into the whole thing. These bubbles vary in size between 0.5 millimeter and 1/3 of a millimeter. Really fine bubbles right through. And if you look carefully, these bubbles also have like holes with adjoining bubbles. They share. The problem being is that when water condenses in the cellular insulation, it forms droplets, and those droplets, this is why we call them droplets, because of the surface tension, they create these little droplets that stay in there forever, practically, right? So, cellular insulation creates a problem of keeping moisture in it. It doesn't allow the vapor form droplets to drain properly. Now, there are familiar names: polyurethane, polyisocyanurate, polystyrene, and all three of those are thermoplastics. So what happens with thermoplastics when you heat them? They become softer, they become liquid, they can reach an ignition point, yeah? And when they ignite, they generate pretty nasty gases. And this is why firemen now they go into buildings wearing full breathing apparatus. Going into a burning building with modern materials, 5 breaths, without it, you're dead. Why? Especially that stuff. Polyisocyanurate. Cyanide is used as stabilizer in it. Yeah? Okay? Nasty stuff. How many people have here seen carpenters, workers on building sites burn offcuts of timber, tannalized timber? Anybody seen it being burned? Yeah, tannolith. Has that cyanide in it besides copper quaternary, right? So nasty stuff being released into the air. They shouldn't be burning it. And this is why treated timber is no longer used in biomass pellets. So out of all of the ones that we are using in construction at the moment, foam plastic, myself personally as a designer, this is the only one that I would specify above ground level, phenolic, right? Because it's a thermosetting plastic. So 2 parts mixed together, cross-polymerized. When it's subjected to extreme heat, it starts to char. It doesn't ignite. Yeah? Next time you've got a chunk of any of those 3, right? A small chunk of it, and you've got a lighter handy, just try the lighter underneath it. You'll see how it burns. Yeah? Just don't breathe the stuff. Right? Quite nasty. So phenolic is about the only one that I would specify above the ground level. Otherwise, below slab, below screed, those 3 are fine. No problems. Yeah? But we're getting on. So, if we're looking at material resistances, this is material resistance for something like aluminium foil, right? 4 million, yeah? And this is why we are using aluminium foil back plasterboard in the kitchens and bathrooms to try to prevent moisture migration. It doesn't fully work because, again, you have to fix the material. So there's nails, there's screws, etc. And then some people also like to put those lovely things called downlighters in there. Yeah? Nice things, downlighters. They're lovely. Especially if they're halogen or even straightforward, you know, straightforward GU10, even LED ones. And by the way, at university I had a couple of big boxes. Now it's reduced to a very small box because one of my students was a maintenance technician working for a chain of hotels, and he convinced a hotel to carry out an experiment. And one level was left as existing, another level was put in as CFLs, and another level was put in as LEDs. And running costs and maintenance and repairs was compared, and a lot of LEDs burnt out, and I had boxes and boxes brought in, which I took apart and looked at the electronics inside, and guess what? Some of them were pretty ropey, especially Chinese ones. Dangerous. So, if we're looking at materials resistance to moisture migration, aluminium foil is probably highest. That's my own experimental figures that have come out of it. EWI is the biggest problem that we are experiencing in UK at the moment. External wall renders, especially if they are using acrylic modified renders. There's nothing wrong with it if you are using it appropriately. External renders for EWI should be either straightforward cementitious based without the acrylics, or they have to be lime based, right? And it would require obviously thicker layer and mesh. But because of that, all of the manufacturers are using what? They're using acrylic modified renders. And these renders come in bags. They just add water to it, put it on several layers because there's base coat layer. Then the next layer is scrim. Then they build it up flat, and then they'll put the final coat. So in effect, it's 3 layers of acrylic material that's put on top. And guess what? You do experiments, and this is the figures that you will come up with, right? It's pretty well vapor resistance, yeah? It's equivalent to painting your building with masonry paint, several layers. Not only 1 layer, several layers. Or it's coming up not too far from polyethylene sheet, right? On the other hand, you've all seen wonderful material called Tyvek, and look at that. Depending on the type of Tyvek, it's either very, very low or slightly higher vapor resistance. Now, vinyl paper, look at that, 60,000 to 100,000. Why? Plastic. And plastic is very much so resistant to vapor passage. By comparison to our traditional material, remember, this was going into thousands. Our traditional materials, brick, 25 to 100. Concrete, 30 to 100. People say, yes, there's waterproof. Yes, but it's not vapor resistant. Yeah? Hardboard. Now, look at the other one. Plywood, OSB. Why is that 6,000? Because of the adhesive in between the layers. It's plastic adhesives. Again, highly resistant. So, by building up different materials within your fabric, you are creating imperious layers, right? So, let us look at the next one. And this is skim, plasterboard, brick. Again, same Victorian building, but now a different salesman's come along and 100mm insulation on top and render fiber cement put on, and I put 10mm just for the purposes of calculation. So now, if I did, this is my structural gradient, this is my dew point gradient, and look at that. There it is, right towards the end of the insulation layer, it is getting interstitial condensation. So my insulation is getting wet right underneath that layer of acrylic render. And guess what? I have photos where it shows the spread of the cold areas over walls. Yeah? I use thermal imaging cameras regularly, and I've been using thermal imaging cameras for years to be able to analyze how buildings behave. There's one. And it is proper thermal imaging camera on a smart device. Yeah? CAT 62 Pro, right? If you want to buy it, it's cheaper than actually buying a separate thermal imaging camera, and it's smartphone with thermal imaging camera. So, one of the things that it demonstrates is that the water starts to condense within that insulation. As it starts to condense, that gradient starts to shift up during the winter. So more and more insulation is getting wet. Yeah? People say, but we don't have that problem in Germany or in Poland. No, you don't have it. Why? You've got low temperatures, -10s, -20s, And what you get with that, you get dry desiccation. This is like coffee that you buy, freeze-dried coffee. Yeah? If you store meat or anything else in a fridge and people say, oh, that meat is gone white, it's actually desiccated. Nothing wrong with it, it's just desiccated. Right? We don't get the low temperatures in UK to dry our insulation. It doesn't happen. So the insulation stays wet for most of the year. After a couple of years, that insulation is absolutely sopping wet, especially on north, northeast, northwest areas of the walls. Okay? South, southeast, southwest fares a little bit better towards the end of the summer. It does help it slightly, but not a lot. So, what happens next is that we bring in render fiber cement, and next we put render acrylic modified. And look at that. And straight away it shifts the dew point gradient to a much higher area of our insulation. So as soon as you introduce acrylic, it's a plastic. Yes? Yes, it is water-based plastic. But once it's polymerized, it becomes quite resistant to vapor pressure. Right? So more of your moisture is caught up in your insulation and it's got nowhere to go. Yeah? And as you start introducing insulation like polyurethane, yes, your U value is much improved. Yeah? Look at that. With rock wool insulation, 0.039 is a rock wool insulation. As soon as you put polyurethane, 0.022, much lower resistance, more energy efficient than rock wool. But it's bubbles. And because of its bubbles, it forms droplets inside and they don't go anywhere. Right? So it creates a problem for us of extreme condensation. So what does it mean? We are introducing a lot of moisture into our buildings. Our buildings are becoming, people are expecting warmer buildings. In the past, Victorians, they used to burn coal continuously. They also had much different clothing factor than what we are used to. They used to have several layers of clothing, quite heavy clothing, even inside the buildings, right? I had a client who came back after enveloping scheme, said, my house is still cold. I'm very unhappy with this. And he was talking to me whilst wearing a string vest. And this was in January, right? So how people live often enough contributes towards a lot of the problems. So it's a clothing factor. The other one is, again, how people are using their houses. Because our environment is better sealed, we are introducing UPVC or aluminium windows that have 3 lots of rubber seals on them. So in effect, our houses are becoming hermetically sealed. The air movement doesn't happen. Yeah? And over a period of a night, each one of us will put approximately between 1/3 to about 1/2 liter of moisture into the air. That moisture has to go somewhere. It has to condense on a colder surface, or it has to go out. And people say, no, I opened the window to vent the bedrooms out. But do you leave the door ajar? And normally I specify and say, at least open 300 millimeters a foot to allow the whole building to normalize. Okay? Not close the doors tight. So 4 people living in a house, this is approximately 4 liters of water that has to go somewhere. yeah, over a 24-hour period. And that's 4 liters of water. This is how many people have, you know, a tank for fuel as a, you know, just sort of a safety measure. So if you run out, you can go on. That's 4 liters normally, a gallon. So it's got to go somewhere. And where will it go? On the colder surfaces around the house. And those colder surfaces, often enough, are the areas that are very contentious. Yeah? Because if you look even in the 60s bathrooms, what was a typical 60s bathroom? A bath, 3 levels of tiles, a sink with a splashback. Now, everybody's expecting the whole bathroom to be tiled. If you're tiling the whole bathroom, what are you introducing? You're introducing impervious surface, like glass, basically. Moisture has nowhere to go, and this is why building regulations recognize that and forcing us to introduce what? Extract ventilation with humidistats, with delay in operation, so it runs until such time as humidity levels drop to about 60%. Yeah? So it's a complex problem, and it's a problem that our way of living and how we are approaching the whole thing is changing things. But what are we doing about it? At the moment, between us, the Quorum Council, because of specific one student who really understood these spreadsheets, and he took it to his bosses and said, look, we need to do something about this moisture in buildings. And UCL, we're working on a program where we are addressing these issues. And over the next 2 years, we will be developing a toolkit to actually train the housing surveyors in understanding condensation and addressing it properly, and developing a toolkit in terms of what would be used to understand and develop all of that. At the moment, we're in a stage where we brought together housing stakeholders, which is not only the council people, but also the tenants. And we explain things to them. This is the process. Do you understand it? How would you want us to explain this to you so it's clear and it can be explained to another person clearly? So at this stage, we are seeking information from stakeholders. Next year, that fancy spreadsheet is going to be put into an application which will make it much easier for surveyors to use, as opposed to somebody like me who does it in great detail. So it will be simplified and used as an app. So watch this place. EPCs. How many people are really familiar with EPC? It's a straightforward one-day course. You go on EPC, use of software. But I've also seen EPCs where on a Victorian building, it's suggested that cavities should be filled with insulation. There's no cavities in Victorian buildings, you know. It's a problem. Those things are not worth anything, really. They're not giving us the right information. So we really need to understand what is happening in our building fabric, in our environment, and how we really need to deal with those problems. Okay? It's quite a straightforward thing if you like thermodynamics, which I do. But for a lot of people, it's a bit of a struggle trying to cope with the whole thing. So standards are being changed. Some people would be familiar with that passive house standard. Yeah? So what are we doing? We're reducing the air infiltration and air changes. Standard British home, somewhere in a region of about 3 ACH. Passive house, 0.6, right? So it's a lot less. But there's also a problem. When you don't have enough air exchanges, you have to introduce mechanical ventilation with heat recovery. What does that do? Moves the warm air out, preheats through a radiator, incoming cold air. A standard thing that people will say, 70% of the dust in our homes is human skin. No, it's not 70%. It's in a region of about 50, right? But guess what? All of that ends up in those ducts. Most of those ducts are ribbed. All of that stuff is deposited inside there. And guess what? All of the moisture and everything else, these are organic compounds. Organic compounds, bacteria, fungi, they're growing on it. I've made a little robot for collecting samples out of all of those. And guess what? Some nasty pathogens came out of it. All right? Yeah? So, MVHR, I have my doubts about it. Right? With the amount of energy that you're saving, it's a token gesture. It doesn't work. So, we are looking at a much better way of approaching, assessing the problems in buildings, especially the older buildings. Newer buildings, it's easier to specify, easier to build, to make them better compliant. Old buildings still remain a serious problem for us as surveyors. And seriously, now that the little boy has died, guess what? There'll be ambulance chasers coming in and latching on to that. Same as PPI or owning diesel or owning MBNA card. They're going to make a fortune out of it. Yeah? All you require will be one of those to come in and take some photographs in your bedroom, in your bathroom, showing mold and mildew, and they'll be going after the landlords, etc. So, not a nice picture for surveyors, especially if you're involved in these areas. Okay? And that's about it. So, thank you. Any questions? Go on.
Someone who doesn't understand any of the numbers that you put up there from beginning to end, you didn't provide any solutions.
The solutions are varied.
Just one other thing, you didn't mention just simple dot and dab. You've mentioned battening, rock wall,
Yeah.
all sorts. Why can't you just take 20 mil plasterboard, silverback, dot and dab? Would that not have any effect on?
It has very, very minor effect on U value. Main thing is why people are going for insulation that creates a problem. It's because of the cost of heating. They need to improve U values. And when they are improving U values, they're creating problems. It's not necessarily dot and dabbing, which is quite a good way, but even that, you still have electricians and plumbers drilling holes through it and everything else. So don't even go there. It doesn't work. Go on.
What's your view on spray foam insulation gloves?
The one that is sprayed, there's two types.
Open and close area.
Yeah, one is polyurethane, and polyurethane, if you've ever seen it up close, when it cures, it has a very, very shiny surface on it. And it's utterly, totally impervious to water vapor. So it keeps the water vapor on this side, yeah? But guess what of the other problems? They normally come in and spray it on straight over the rafters, yeah? There's another engineer. An engineer will tell you that the timber moves seasonally. As the timber moves, it actually moves and cracks the polyurethane. And that moisture works through those cracks, filling up the voids behind it. And because there's no air movement against the timber, that timber rots very, very fast.
What about the open cell type? What's your view on that?
Open cell, it still is the same evil. All you're doing is just dressing it with a different name. Yeah.
Okay, just too quickly, when you explain why you don't like heat recovery, are you proposing just a straightforward vent or humidistat instead?
The best approach is ventilation with humidistats.
Okay, and what do you think about vapor open systems, breathable systems like sheet wool?
Right. Again,
Wood fibre?
any organic material, sheep's wool. What is sheep's wool? Keratin. What is keratin? It's a protein. Hey, something wants to eat it. Yeah? It's like meat. Makes no difference. Poisoned. Stop calling it treat. It's poisoned. Yeah? It's poisoned. Period. There's no other name for it. Poisoned. Yeah? Makes no difference whether you are using cellulose fiber, you're using hemp fiber. What is that? Up to 70% cellulose. O's, sucrose, lactose, fructose, sugar. Hey, you know, something wants to eat that sugar. It's a nice dessert after the keratin. You're going to treat it? No, sorry. You're going to poison it? Yes. Go ahead. And then there's clever people who are starting to now mix different materials together. Yeah? They take hemp, they take cement, and mix it into a concrete block. Wonderful, isn't it? Organic compound. It's hygroscopic, right? Organic compounds, especially wood compounds, in the presence of oxygen, they break down, they generate acids. Acid within the cement matrix, which is alkaline, what are you doing? You're building in self-destruct. I don't need to tell you any more than that. This is science.
I think we should have this conversation in 10 years and I'll tell you when my house has fallen down.
Go on.
I'm interested to hear your thoughts on, say, a Victorian house. There's a render applied externally which is waterproof and obviously prevents the wall from breathing.
Yeah.
Would you recommend to the owner that it was removed, that render?
This is one of the problems that often enough, trying to remove it, you will cause serious damage to the render and to the insulation itself. So you need to completely replace the whole thing, really, at the end of the day.
So take it off?
Take it off and put something which is breathable. There used to be a system called mesh system. It was marketed by MacArthur company, and what it was rock wool with building paper and stainless steel mesh, and it was straightforward sand cement render over the top of it. That was, in my opinion, the best system ever. Right? Nothing else came close to it. Yeah.
I work quite closely with, best way to describe them as ambulance chasers, who work closely with tenants that are after local authorities and all the rest of it, chasing primarily for condensation, damp, mould, and all those things. So this subject is just the most interesting subject. But you've blown a number of so-called solutions that we would put forward to the freeholder or the landlord out of the water there, which leaves me and a number of others with a problem as to what we can
and
suggest.
This is why
how they would go about it. And one of the main things for a lot of the councils is that they have concrete buildings that have a clad with brick and all the rest of it, but thermal passage through the concrete elements, which basically are concrete on the outside and concrete on the inside with a thin skin of glass on it, and the cold just basically transfers straight through the building
That's
and
right.
into the person's property.
That's
and
right.
then they're dripping with condensation, then mould, and then all the other issues that come with it. I don't know, but you've blown, one of the things what we kind of head towards if we can't find any other solutions is additional ventilation, mechanical ventilation,
Yes,
passive
it
air
works.
systems, all those things. But you've thrown them all out. So,
This is
I'm
why.
concerned as to where we would go.
Ventilation he was okay with.
Yeah.
Yeah, I mean, you know, whether it be new build, old build, Victorian.
And there is very much so hit and miss approach at the moment to control of condensation. There's anything from one so-called consultant to deal with mold that comes in and washes the walls with distilled water. I don't know why distilled water doesn't work. To another one that will come in and wash the walls with boric acid, right? Okay, boric acid, borax. This is the stuff that's often enough you'll see in washing powder, etc. Right? Again, works against mold and mildew very well, but at the same time, boric acid present in the environment is not particularly good for us. Yeah? It's also used as a fire retardant. How many people remember these sofas that used to burn people's skin? Anybody remember those? Leather sofas that burned and left people with burns, because it's also used as a tanning compound.
Just one other thing though. You touched on it, but you didn't go too deep in it. The human element of condensation build-up within the property, is that something that we can look at?
And this is why
drawing that moisture, collecting it during the night when there's 2, 3, 4 people sleeping in a flat with 2 or 3 bedrooms.
Yeah.
You know, that moisture that gathers in there, you can see it in the mornings dripping down the walls and all the rest of it. But if we come along then and test it at 10 o'clock in the morning, we're going to get readings that are useless really, because there's so much condensation running down the wall from the human element.
Yeah. Again, this is why we are working at the moment with stakeholders to be able to, we gather them into groups and we explain, this is a condensation problem, this is our advice. Do you understand why we are advising? I go through a simplified version of this, explaining it to the tenants and explaining that ventilation is necessary, opening doors and leaving doors ajar is important.
But in the current fuel crisis,
this is the biggest problem.
They don't understand the sense behind leaving the window open and seeing their fuel go straight out the window, particularly when they're spending £10, £15 a day to heat their property.
Yeah, this is one of the biggest problems. Yeah.
I was going to ask that,
Go
actually, how much of the problem could be solved by just getting people to use the houses properly, not turn the fans off, not keep the windows completely shut, have them in background ventilation.
It's much, it's much easier in a house. It's more difficult in the smaller areas like flats and apartments, right? Because there it's a problem, first of all, with new building regulations. This is why the new building regulations are looking for cross ventilation, right? It's very difficult to achieve cross ventilation in apartments. Very difficult.
Because they're single-sided.
Yeah. And this is why if you have a look at the way apartment buildings are built in the United States and Canada, what you will find is that in a lot of those buildings, they have service shaft and ventilation shafts between the apartments. And those ventilation shafts, they provide cross ventilation. It doesn't exist in UK. Right? It's not applicable to UK. But in Canada, United States, it does exist. And that reduces the problems. Yes.
So as I understand it, your sort of hierarchy of good and bad insulation, you've got Rockwell the best. Would you say fiberglass insulation is similar to that?
Fiberglass, there's one problem with fiberglass, and that is they use a resin epoxy which is bonds the fibers and keeps them apart. And unfortunately, that is quite flammable.
Yeah.
Yeah,
But
and this is
because-
rock wool.
okay.
This is why I specify rock wool, because it doesn't have that flammable resin adhesive in it.
So going from best to worst then, the phenolic one.
Phenolic is,
what's the
as I said,
brand- what would be a brand name that we might have?
there is various makes, but you have to insist and say, no, I want to see manufacturing sheet phenolic. It
So
has
if you
to say
went to
phenolic.
Kingspan or Celotex, or
Celotex-
they might do a phenolic one,
Yes.
but they prefer to promote the PO ones or
Yeah.
PIR ones. Yeah.
Because they are cheaper.
Yeah, okay.
They're cheaper to manufacture as well.
So these are all flammable, aren't they, these foams? I mean, I've done a refurb, I stuck it all on the barbecue, and all the foams are just...
Yes, they'll go up. As I said, if you have a little chunk of it and put a lighter to it, you'll see it goes up like black powder.
I did my master's dissertation on internal wall insulation. That's of
Yeah.
interest because of the conservation area, but external is the same. And I had to interview Phil Heath at Kingspan and the Senator
Yeah.
Sky, and they will say, I said, yeah, but aren't these things flammable? They're saying, yes, but it's okay, we've got an aluminium foil on the outside. so let's not cut into it. Well, Grenfell,
Yeah. It's the same as any engineer will tell you. Recessed lighting is the biggest problem, and you would have seen scorched timbers from recessed lighting. I've seen scorched timbers, and if you have any of those 3 thermoplastics, you're just asking for a fire. You're asking, because some of them, the ignition point is just in a region of about 100 odd degrees. Right? Once it starts melting, boom, next thing is flash point. Dangerous.
So, one more question.
Last question.
Elementary, silly science question, but you know heat rises.
Yes,
Does vapour
it's called convection.
Does vapour rise as well? Or is that-
As the air rises, it moves the moisture with it.
So your vapour barrier in the ceiling is more important than your one in the wall, is it?
Makes no difference, because you have convection happening, and what is happening with the moisture, that pressure is trying to neutralize, right? So move from the inner side to the outer side. So it makes no difference whether it's ceiling, all the walls, it will move through,
Okay. Yeah.
right?
Yeah.
Okay, thanks very much.
Very good.